In section 1, called the definite integral, we are going to get to the point where we can describe and execute integrals, but before we can get to that point, we need to kind of talk and wave our hands at and look at some situations and see what's going on so we can kind of move to that overall concept of integral. And that's going to be one of our big concepts, not only for this chapter, but for this course. And so let's look at the first example. It says, suppose a car travels on a straight road at a constant speed of 40 miles per hour for 2 hours. See the graph of its velocity. How far has it gone? Well, if we remember, distance is equal to rate times time. So this one's pretty easy. The car has gone 40 miles per hour times 2 hours, so we get our 80 miles. And this is by going our 40 miles per hour times 2 hours, and that's where we get our 80. Now, if we look at this example, we can see that it was just pretty simple of length times time. Now, that's not always the case, so let's look at our next example. Now, suppose that a car travels so that its speed increases steadily from 0 to 40 miles per hour. So you can see that that line is a slope that's increasing for 2 hours. And it says, just be careful you weren't stuck behind this car on the highway. See the graph of its velocity below. How far has this car gone? So the trouble with our distance equal to rate times time relationship is it only works if the rate is constant. With this one, that rate is changing in every moment as time goes on. So there isn't a good way to use this formula. We would have to approach it a different way. But if we look at the graph from the last example, and let's scroll up to that, we notice that distance equals rate times time also describes the area between the velocity graph and the axis of the time. So between 0 and 2, the rate is the height of the rectangle that is being formed. The time is the length of the rectangle, and the distance is the area of the rectangle. And so when we did that 40 times 2, we actually were able to get this entire area underneath here, and that was our velocity. So this is going to be the way that we can extend our simple formula to handle more complicated velocities. And this is the way we can answer the second example. So if we consider that our length times width on that rectangle and the area of that was created was our velocity, we could do the same thing here. And we can see that this is a triangle, so we could do base times height divided by 2 and also get this area underneath here. So we have 2 hours multiplied by the 40 miles per hour at that highest point on our triangle divided by 2, and we get that it traveled 40 miles during this time. Now, this was a specific example dealing with velocity and trying to find that total difference traveled, but let's think about it in a more general sense, and let's look at this graph here. It says, if we were looking at the curve being our function with relation to time, we look at our y-axis as our rate, and we look at our x-axis as t, then any area underneath that curve would be the total accumulation of what we're dealing with. And so this could be for other rates, such as the production of a factory, bicycles per day, or the flow of water in a river, gallons per minute, or traffic over a bridge, cars per minute, or the spread of a disease, newly sick people per week. The area would still represent the total amount of something. And that's the big idea that we're going to be looking at. And so let's look at this example. It says the graph below shows the flow rate, cubic feet per second of water in the river at the town of Gold Bar in Washington State. So you can see red is our function. You can see our time is on the x-axis down here. You can see 1,000 cubic feet per second is on your y-axis. And so if we wanted to figure out what this area was representing, this area of the shaded region represents the total volume or cubic feet of water flowing past the town during the month of October. And we can approximate this area to approximate the total water by thinking of the shaded region such as a rectangle with a triangle on top. And knowing what we know about our basic shapes from previous courses, we could simply calculate that. The total water would be the total area or area of our rectangle, add it to the area of that triangle. Following suit, you can see our calculations here. And so we come out to be about 7 billion cubic feet of water flowing past Gold Bar in October. And so I I didn't want to gloss over those calculations, but I'm pretty sure you could do those yourself. But I want to kind of break this down and show you in a different situation on how that area is being created. Now, we're not going to be always working with rectangles and triangles. Those are really nice functions. This one, obviously, is not exact with that triangle, but just giving us an idea of a different situation. And so this brings about a big concept that's going to lead into what we need. And so there is a way of calculating this area under a curve. So let's just take a basic curve here, and I've drawn it repeatedly to kind of show you some things. And so if we were approximating with rectangles, there are different approaches or different ways of thinking and formulas that could go with this. If I take any given curve, and I've just taken the same curve and copied it down as we went, and I'm going to create some rectangles to go with it. As we're creating these rectangles, these are called Riemann sums, and there are calculations and formulas, but I think it would be more profitable to us to just kind of talk about the idea instead of spending our time executing it repeatedly, especially over some homework questions. So I just want to gather up what we're talking about, and then I'm going to show you how this relates to what we're going to do. But we are not going to practice this or even exam over this concept, but it's going to help us to see the next part. So these Riemann sums have these methods of creating rectangles underneath of it, and they've done it like 3 different approaches. They do one where you take like the left side of your rectangle and you line up these rectangles here, and you take rectangles because you know the formula for rectangles, and they just said if we line up rectangles all along the red curve, so like the left hand corner is on the red curve, and we calculate all these rectangles length times width and we add them all up, then that will give me an approximation of the rectangle. Well, then another school of thought is, well, what if you line them up on the right hand side? Because you can see I had some excess area up here, and underneath here was under approximated. So what if we look at lining up the right corner of each of our functions to the curve, and you can see creating those, we still have some overage and still some underage. So we could do it from the left. We could also create rectangles from the right. And they said, you know what, that's not really the most accurate way. Really, the midpoint would be good. So if you're drawing rectangles, the midpoint of the top of your rectangle needs to be on the curve, and this would better satisfy losing a little and adding a little, and that would balance out. And then really, whether you're doing left, right, or midpoint, the amount of rectangles you create is going to give you the best area. Because you can see here, if I just have 3, I have big chunks not there or missing some here and there. So they said if they just take a lot more rectangles, obviously the area of margin here would be less, and we'd be a lot more accurate. And you could even take this even more times, or if you consider what we did in last chapter, taking the limit as these rectangles get closer and closer to infinity, so taking more and more and more and more rectangles, you can imagine how accurate those rectangles would get closer to. Now again, I want to talk about this and show you these left-hand endpoints, right-hand endpoints, talk about Riemann sums and averages, because it's going to lead us into a bigger concept. And so if we take the summation of our height of our rectangle times the width of our rectangle, and we add all these up, and this gives us a delta notation. If we take and make our rectangles and add in more and more and more, basically getting smaller and smaller and smaller, this is going to lead us to the area under that curve in a more defined value than just approximating it. And that is what Riemann sums is doing. So here's a nice block from your textbook. It says a Riemann sum for a function over an interval is a sum of areas of rectangles that approximates the area under the curve. You start by dividing the interval into little subintervals, and that's creating your rectangles. Each subinterval will be the base of one rectangle, and we usually make all the rectangles the same width, delta x. So the height of each rectangle comes from the function, and we talked about evaluate which point, either left point, right point, midpoint. And this brings in a new notation. And I do want to expose you to this. This is the sigma notation. This is it written a little bit nicer here. And it's just adding up all those rectangles. And so it says this is read as the sum as I equals 1 to n of x sub I delta x. The I is a counter, like you might have seen in maybe a programming class if you've taken that. And so this is what Riemann sums are, and it's using that sigma notation to sum it all up. And the whole reason we would look at this in section 1 is to expose you to it, work with it, and then go, hey, here's a quicker way of doing that. And so that's what I'm going to jump to here, the quicker way of doing all this. This gives us the definition of a definite integral because the area under the curve is so important. It has its own special vocabulary and notation. And so what we want to do is we want to find the area under the curve of that function exactly to the decimal point of what it is instead of approximating it. And so this is this idea of a definite integral. It's the area under the curve. So let's we haven't used this word integral. Let's kind of define this, talk about this, and also pick up our new notation. The definite integral of a positive function f of x over an interval a to b is the area between f and the x-axis, and it's restricted between a and b. So it has a left hand and a right hand, and we're getting the area underneath it as it goes to the x-axis. The definite integral of a positive function from a to b is the area under the curve between a and b. Now our notation for this is this little elongated squiggly s is your integral sign. It says from a to b. You read it from the bottom to the top, and the symbol is called the integral, and it basically stands for sum. This also corresponds to the delta from the Riemann sum. The dx on the end must be included. The dx tells us what the variable is, and in this example the dx on the end must be included because it's the variable x. It corresponds to the delta x from our Riemann sum. The function itself that is next to it is known as your integrand, and a and b are called the limits of integration. The book goes on to say, we integrate or find the definite integral of a function. This process is called integration, and this is what we were referring to with those Riemann sums, taking the limit as those rectangles approach and get smaller and smaller and smaller, so multiple rectangles, getting an infinite number of them under the curve, is equal to just the integral of that function. So it really makes our process a lot quicker. Instead of drawing a bunch of rectangles and adding them all up, we just create a bunch of them up to the infinite point and calculate it from there. So let's look at this example here. It says the graph shows y equals RT, the number of telephone calls made per hour on a Tuesday. Approximately how many calls were made between 9 and 11? Express this as a definite integral. So we are wanting to find from 9 to 11, and we're wanting to find this area under the curve. And so all we want to do right now is set it up. In future lectures and conversations, we are going to figure out how to find this to the decimal point, but right now I just want to work on the setup. So this would be the integral of 9 to 11. Our function within here would be our r of t function, and then we would say dt because that's the variable that we are relating it to. And so that is just our setup. Express this as a definite integral. This would be that integral. And again, we're going to move forward and look at how to actually solve these out and find that area under the curve. But for right now, I just want to do one and show you the setup and where these numbers would come from. Here's another example. Describe the area between the graph of f of x equals 1 over x, the x-axis, and the vertical lines at x equals 1 and 5 as a definite integral. So again, just setting your setup. So here would be your integral sign, 1 to 5 of the function with respect to x, because that's our variable. It is blocked off from the x-axis. That's why we just do the f of x, and we'll talk about that again in future sections. The vertical lines, 1 to 5, are our upper and kind of lower boundaries on this definite one. And to make it more specific, we could say 1 to 5 of 1 over x dx. And that would just be the setup of finding all the summations of the rectangles underneath that curve between 1 and 5 and setting up infinite amount of rectangles to get that area to be exact. Let's look at this example. It says, using the idea of area, determine the value of 1 to 3 of 1 plus x dx. And it says, remember that this represents the area between the graph of 1 plus x and the x-axis. So this is this blue shaded region, the vertical lines of 1 and 3. Now with this one, since these are legitimate rectangles and triangles, we could actually break this down and figure out this value. We could create a rectangle here. You can see it has a width of 3, a height of 2, so we have a value of 6 in here. And then we could also figure out this part here up in the triangle and go, okay, well, it has a width of 3 and a height of 2, so that would give me 6 divided by 2 to give me 3. So that total area underneath there would be 9 square units. And so we can, with given functions, actually find the accurate value without actually going into the formalities of integration. But again, right now, I just want to kind of set some things up for you. Now, we can't be in business calculus long without going into some of our business terms. So it says, suppose M of R of Q is the marginal revenue in dollars/item for selling Q items. And if you remember from the previous chapter, whenever we see this word marginal, that meant we were taking the derivative of a revenue function. So it says, what does the integral from 0 to 150 of MRQ dq represent? Well, this represents units of dollars per item times items, so it means dollars, and represents the accumulated dollars for selling from 0 to 150 items. That is, the integral is equal to the total revenue of 150, the total revenue from selling those 150 items. And so we are going to see a relationship between that marginal revenue going back into our total revenue, and then this giving us kind of a span of how many items we were looking at. So this area in the curve is going to have multiple meanings for us as we move forward. It's going to have multiple ways of helping us with different application problems, and it all kind of stems off of finding that area under the curve, Riemann sums not being as accurate because there's approximating. So let's move forward and also find some better ways to find those values.